Before we start with the webinar, I would like to set the frame of this event within the work of Forest Europe and briefly introduce you to our current approach of establishing a forest risk facility. So the Forest Europe, you may have heard of it before, is formerly known as the Ministerial Conference on the Protection of Forests in Europe. It originated in 1990 to improve the concerning status of European forest vitality as a consequence of industrial emissions. Today, it has 45 signatory countries and the EU as members, as well as many observer organizations such as PFC, FSC, CEPF, and USDA4. Since its origin, it is well known for the definition and the concept of sustainable forest management, its criteria and indicators, and the report on state of Europe's forests that is published in collaboration with FAO and UNECE every 5 years. It also led to the establishment of UFOGEN in 1994 with a valuable role in conserving forest genetic diversity. The chair of Forest Europe is rotating within its members, the chair until 2025. Next slide, please. During the German chairmanship, the work focused on the establishment of a forest risk facility. Due to the increasing effect climate change has on our forests and the dramatic damages experienced all over Europe, Ministers for Forestry agreed in 2021 to work towards the establishment of a pan-European forest risk facility under Forest Europe. In recognition that forest damages do not track or stop at national borders, it should serve to connect national experts, share and exchange knowledge, and build capacity for prevention, preparedness, recovery, and response at pan-European level. During the last 1.5 years, a pilot for this forest risk facility was running, focusing on wildfires, bark beetle outbreaks, and windstorm events as major abiotic and biotic forest risks. Throughout workshops and expert meetings, published and summarized in policy briefs with recommendations for policymakers and as useful guidelines for practitioners for national implementation. All material is available on our Forest Europe homepage. The address you can find on the lower side of this slide. During various meetings, the added value of and its efficiency and effectiveness were recognized, and we are preparing the documents for the full-scale launch of such a facility after 2024, which will be decided at the Ministerial Conference at the end of this year. We continue with our important work, raising awareness for forest risks, connecting science, policy practitioner, and the public, with a focus on one of the major threats to forests today, drought stress. Next slide, please. Starting a webinar series on this topic, we recently held a webinar focusing on the importance of genetic diversity for adapting forests to drought and secure healthy forests. We did learn about the physiology of trees during and after drought, what happens to trees under drought, and the differences of tree responses to drought. We also learned about the genetic basis of such variations. How does drought stress vary among species, among populations, among individual trees on the example of two Mediterranean pine species? We were able to get an insight into epigenetics and were offered a vision of the ongoing genetic research carried out in arid to semi-arid areas in Turkey. Presentations, a summary report, and the recording is available on our website. Next slide, please. Today, we continue on the topic of drought stress, looking at measures we might take at regional, national, and international level to support Europe's forests to adapt to drought, to unravel the science behind these recommendations and provide practical guidance. With this, I would like to come to our first presentations, given by Ansgar Kamen, Professor for Physiological Plant Ecology and Head of the Department of Environmental Sciences at the University of Basel in Switzerland. As plant scientist, he is interested in the ecophysiological processes in plants that determine the fluxes of water, nitrogen, and carbon in terrestrial ecosystems. He seeks to understand how plants function in the context of their environment and to reveal how plants shape the functioning of ecosystems, as well as the provision of ecosystem goods and services that human societies depend on. Today, he will share results from his research looking at the extreme drought event in 2018 in Central Europe and its devastating impact on beech forests, to discuss the vulnerability of European beech, but also if recovery is possible. The floor is yours. Please share your screen. Thank you.
Thank you very much. Before I start, there were some issues with the sound, also indicated in the chat. My question is, can you hear me and can you see my slides?
Yes.
Okay,
yes.
Perfect. So first of all, I'd like to thank the organizers of this webinar for giving me the chance to talk here this morning and to share some of my research. What you can see here as my cover image is our research site in the Jura Mountains in Switzerland, where we have the possibility to assess the physiological responses of a whole range of different tree species to drought events. Now, what you can see here is a winter image. These trees are not dead, but it illustrates that this is a site with very high species diversity. The motivation of our research is driven by these events. You're all familiar with climate change, so I don't need to go into much detail here, but there are still a few things that I would like to point out. These are climate data for the summer months of June to September for my hometown in Basel. And what you can see here, if we just look at temperature, that since about the 80s, we've seen a steady and progressive increase in temperatures. And if you look at the so-called extreme events, and I'm supposed to talk about the 2018 events today, we can see that 6 out of the 9 hottest summers during the last 120 years have occurred in the last 9 years. So it's a bit difficult for me today to isolate the 2018 event from this whole series of events that have occurred. I think that is, first of all, a very important message, and I will get back to that in a second. Second of all, we can see is that with respect to precipitation, we're actually seeing less dramatic changes. The question, though, is why are we still talking about drought and progressive ecosystem drying? Well, the drought that we are seeing mostly comes from changing atmospheric conditions, indicated by the so-called vapor pressure deficit, which describes essentially the atmospheric vapor demand of the atmosphere. So how quickly can the atmosphere actually dry out an ecosystem? That's what this is actually indicating. And again, what you can see here is that the extreme years, the driest years, severely accumulated in the last decade, and we can also see a progressive trend here in atmospheric drying since about the 1980s. Just this week, the federal government of Germany has released the annual forest report, and I think this matches very nicely the climate data that I've just shown you. Now, the second amendment to my talk, where I'm supposed to talk about only the 2018 data, which I cannot isolate from the other events, is that I'm supposed to talk about beech trees. But I think to understand the biology of beech trees and the response of beech trees to climatic change and to extreme climatic events, we have to put it into the context of other species. Now, what beech trees shows us, and essentially this is the state of canopy health. So with everything that is red indicating severe canopy decline, everything that is in orange, we call this a warning level, so where canopy decline is being visible, but it's not very severe yet, and then green essentially means healthy trees. What we can see in these figures is that since the 80s, when these assessments started, we see a progressive decline in healthy trees and a progressive increase in trees with severe canopy damage. What we can also see, if we pay very close attention, that some of the extreme events that we are aware of, for example, the 2003 event, caused a step change where trees hardly recovered from. You can also see this, you can see this here by looking at the category of healthy trees, and you can also see this here by the category of damaged trees. Also, the recent 2018 event and the progressive extreme events after that caused a step change where on average there are more severely damaged trees today than there were in the past 45 years. Now, if we compare this to spruce, the pattern is a little bit different. If you look again at, first of all, the trends are much less distinct, except for the last couple of years where we had these extreme hot and dry summers. And what you can also see is that the individual events like 2003 caused a deterioration of spruce trees in the following year, but there was some sort of recovery. Now, since we haven't had any wet years for a while, we actually also see a deterioration in spruce trees. But the patterns, if you compare these two graphs, are different because between these two species, and I will elaborate a little bit why this is. We can see the same in mortality. And I would just like you to look at the beech trees in this graph. This is actually the mortality of trees, of this, deciduous trees across Germany. Just look at the dark line here. So this is beech. The background mortality is relatively low. And what you can see is that since 2018, mortality has increased and mortality is sustained above the background mortality levels. If you compare this with spruce, background also here, the dark green line here, background mortality in spruce also was very low in the past, skyrocketed after 2018, but different to spruce, to beech, where the mortality is sustained, it then declined in 2023 and leveled off. So the response pattern of these trees are very, very different, indicating a different biology. To understand this biology, we need to understand what's actually happening in a tree when it's exposed to drought. So we need to look a little bit at plant-water relations. As soon as a tree opens its stomates, it loses water from the leaves to the atmosphere. And the drier the atmosphere, so the higher the vapor pressure deficit in the atmosphere, the more water is lost from the leaves to the atmosphere. Now, this loss of water causes the drying of the leaves, which then causes what we call negative pressure or negative water potentials in the canopy. And this water potential you can imagine as a force that is pulling water through the soil-plant atmosphere continuum and extracts water out of the soil to replace some of that water that is lost from the leaves as soon as the stomates open. This process is fine and well established, but the trees run into problems if either the evaporative demand in the atmosphere is getting too high, or if soil moisture gets so low that it cannot respond to these negative pressures or to the suction force. And this then leads to two negative pressures, too much tension on the vascular system of the trees, and an interruption of the conducting tissue, so a breakdown of the conducting tissues. We call this embolism formation in plant physiology, which essentially interrupts the flow of water from the soil to the canopy. We can use very simple tools to actually quantify this disturbance of the conducting tissue in tree branches by collecting tree branches in the field using, for example, our canopy crane, placing them into a dye like this methylene blue solution that you can see here. We wait for a day until these branches have transpired in the greenhouse and have sucked up some of this water, and then we make cross sections and we look at these cross sections under the microscope, and then we see images like this. And what you can clearly see here is an intact branch where the entire vascular system is intact, so water indicated with a dye was transported in the entire vascular system, while you see an impacted or drought damaged branch here where only a small fraction of the conducting tissue is actually left. Now, how did tree species respond in 2018 at our research site to the severe drought? And there are two very interesting responses that we saw. First of all, so what this figure shows you here are several tree species that we investigate at our site, conifers and angiosperms. And what's indicated here on the y-axis is the percent loss of conductivity. So the extent to which the vascular system was damaged and interrupted by the severe drought event. And what we can see is that in some spruce trees, we saw severe damage, so where 100% of the conductive tissue was interrupted. But some spruce trees actually survived and were hydraulically completely intact. So no indications of drought damage. Now, interestingly, these trees died within a few weeks after their hydraulic tissue was interrupted, and these trees survived. In the angiosperms, Carpinus, but in particular beech, which is the species that I'm supposed to talk about today, we also saw a severe damage of the vascular tissue, but not the entire vascular tissue was damaged. So we saw interruption of the vascular transport between 20 and 80%. So the first question that rose from these patterns is, why are some species like spruce and hornbeam and beech susceptible to drought, while other species, in particular pine and maple at our site, were not? Well, if we look at the rooting depth using stable isotopes, or what we call the root water uptake depth from the soil, we can see that those species indicated in red here that are particularly vulnerable to drought are also those species that have very shallow rooting systems and that run out of water first. While those species that made it through the drought without damaging the vascular tissue are also the ones with deeper rooting systems, in particular quercus, but surprisingly also maple or sorbus terminalis here, and therefore showed very little damage. So rooting depth and the acquisition of deep soil water seems to be the primary driver of drought vulnerability in mixed forests in Central Europe. Now, the second interesting thing, and I've already indicated it earlier, that we see from this figure, from this drought impact on the vascular tissue of the different tree species, is that the response pattern look very different. While in spruce, we have this very strong dichotomy where some trees are completely intact, and those are also the trees that survived the drought without any significant damage. Other trees were completely damaged, and those are also the trees that died within a few weeks after these damages were detected. Now, in fagus or beech, as I said before, we did not see this dichotomy, and we did not see trees that were 100% damaged. We also didn't see any trees that were partially intact. So none of these trees died immediately, but all of these trees showed severe symptoms of canopy defoliation. And those of you who go through forest with an eye open have probably seen these symptoms in August of 2018. This is what many of our beech trees looked like in 2018. And also we saw these symptoms in the progressive years, in particular also last year in 2023, which in our region was particularly hot and dry as well. The question that we have is, can these trees recover from this damage? So we took a lot of photos, and georeferenced photos, and then in 2018, at the peak of the drought, and we repeated this photo session in July or in June 2019 to see if these trees had recovered. And the majority of these trees, to our surprise, because my hypothesis was that these trees will rapidly recover over the winter when the soil is wet, and also in the spring when there's typically plenty of water available in the soil so that they can repair these embolisms. We actually found that the majority of the canopies looked like this. So there was a strong legacy effect of the 2018 drought into the spring and early summer of 2019. So we also quantified this by, again, looking at the loss of hydraulic conductivities in healthy and in the symptomatic branches throughout the 2019 growing season to test if trees can actually repair these embolisms and restore the hydraulic conductivity in their impacted canopies. And what we found, and this might be a little bit of a complicated figure here, is that trees that were symptomatic, so that looked like this throughout the 2019 summer, kept having very high losses of conductivity in their conducting tissue throughout the entire season, while trees that had a healthy canopy also showed some extent of hydraulic loss of conductivity, but to a much, much lower extent. If we now relate this loss of hydraulic conductivity, so essentially look at the fraction of active xylem area, or even quantify the active xylem area, look at just the area of how much tissue there actually is that can conduct water through the stem or through a small branch into the canopy, and then relate that to the amount of leaves that the canopy can support, we find a very nice and tight relationship. So the foliage area of the branch, or you might even upscale that to the entire canopy, strongly depends on the amount of intact xylem area or the amount of intact conducting tissue. To support a fully healthy canopy, as I indicated here with these images of these shoots here, you need a fully healthy and intact conducting tissue in the branches. And this also explains why we see canopy dieback and defoliation following 2018 not recovering very rapidly. Trees were not able to restore the hydraulic capacity of their stems, and as a consequence, they were not able to support the fully developed canopy with water and had to abandon a lot of their buds and not unfold a healthy canopy. The question is, does this matter for the health of a tree? And are trees that have an impaired, defoliated, and partly died-back canopy, are they at a higher risk of mortality? There is a nice paper led from the group of Tom Wohlgemuth based on a study called the 1000 Beech Project that was launched in 2018 at the peak of this 2018 drought in 3 areas of Switzerland, around Basel, around Zurich, and around Schaffhausen, where trees with an intact, healthy canopy were monitored and marked and compared to trees with a heavily defoliated canopy, as I've shown you before. And these trees were then revisited in the following years, in spring and summer of 2019, spring and summer of 2020, and also summer of 2021. Now, what you can see here is that for those 3 regions indicated by the different colors, the 2 categories of trees indicated by circles and triangles. The circles were the ones that were heavily impacted by the drought in 2018, and the triangles were the ones that were controls. If you now separate it by the different regions, for example, looking at the region of Zurich here, the trees that made it healthily through the 2018 drought showed no signs of increased mortality in the following years, but while those trees that had an impaired canopy showed significantly elevated signs of mortality. And the same was true for the area of Basel-Land, where there was a slight increase of mortality in the healthy trees, but a much higher increase of mortality in the trees that were impacted by the 2018 drought. So strong legacy effects, not only on canopy health, but also on mortality. The last point that I would like to make is that we've seen now that the 2018 drought, but also the drought events that followed after 2018 significantly impacted the health and the mortality of beech stands. The question is, how is the spatial variability of these events? And I'd like to refer to a paper from Christoph Leuschner here that was published only recently in Forest, where he looked at the symptoms of drought-induced canopy damage, but also mortality, spatially distributed across northern Germany. And what you can see here, these are long-term records of canopy damage and also mortality, that mortality rates, but also canopy damage is not spatially equally distributed across a geographic region, in this case, northern Germany. So if you look at this figure here, this red line indicates the area of Sachsen-Anhalt, which is this part here of northern Germany. You can see the coast here. Denmark would be up here. Only in this area, this 2018 impacted the canopies and also the mortality of beech trees, while in Lower Saxony and also up here in Schleswig-Holstein, no significant changes in canopy health and also mortality were observed. Now, interestingly enough, if we look at the long-term growth responses of these trees, so these are now the trends in growth from 1983 to 2017. And the background of this map that you can see here is the summertime precipitation. With blue are the areas that have a higher summertime precipitation, and red are the areas with a lower summertime precipitation. And the cutoff here is a 350 millimeter line. And you can see that in these areas that receive sufficient summertime precipitation, so more than 350 millimeters, we see a tendency of, or there are more sites where actually trees have a positive growth trend, so growth is actually increasing, while in areas where summer precipitation is below 350 millimeters, we see actually negative growth trends indicated by these red arrows here. So the point here is that climate change impacts on beech trees are spatially explicit and are largely driven on the one side by the amount of precipitation, and the additional variability that you can see here is also then driven by other adaptive factors such as soil depth or soil texture. With this, I'm already coming to the end. So what I tried to show you is that temperature and VPD increases since the 1980s have caused a decline in beech vitality across Europe. And I think we have now very good time series that are very robust so that we can actually rely on these data. From our own research, we can say that drought events cause the partial and importantly, the irreversible loss of hydraulic conductivity in the canopy of beech trees. And that beech, but also spruce trees, are particularly vulnerable because of their shallow rooting systems. Now, what I show you is that this loss of hydraulic conductivity causes canopy decline and canopy dieback, and that it increases the risk of mortality in beech stands and partially explains why we are seeing a progressive deterioration of beech health throughout Germany. What's important is that these drought and climate change responses, although we see general overall trends across Germany, they are spatially quite variable and depend on the amount of summer precipitation and also soil adaptive factors. Now, a last point that I would like to make is that if we look at the climate patterns, we need to be very careful to treat the 2018 event as an isolated disturbance and now talk about recovery. Because 2018 was not a disturbance by definition. It was just one event on a whole trajectory towards a new, warmer, and also from an atmospheric perspective, drier climate. So it's difficult to talk about recovery because we're not returning back to the current or to the long-term background climate. We are on a trajectory of change, and what we've been seeing in the past couple of years is actually exactly what climate models predict for our areas. So the question is not so much, can our trees recover from this extreme 2018 event, which was actually followed up by another extreme event, but the question is, what is the acclimation potential and the adaptation potential of these trees? And I'm very much looking forward to my successive speaker who will talk about this a little bit. So from my perspective, the key questions that we need to address in the future are, what is the acclimation potential of established trees? So what is the phenotypic plasticity? And given the fact that these trees have been facing warming and atmospheric drying for the past 40 years, I think that the phenotypic plasticity and the acclimation potential is probably not very high. This leads us to the adaptability of beech populations, and in particular to population level genetic diversity, which we have seen through provenance trials is actually can be quite substantial. And we need to look at the next generation and see how does the next generation of trees express this genetic potential and is potentially more adapted to this new climate. And then finally, we need to look across populations and look at the genotypic diversity across different proveniences and think about ideas of assisted migration and try to introduce some of these more adapted genotypes into our environments. I think these are the two or the three important pressing questions that we need to solve in order to answer the fate of beech trees for the future. With that, I'm at the end and would like to close here.
Thank you very much for this great presentation and for these insights into your research. I hope the connection is now better and you can understand me.
Yeah.
I would like to introduce now our next speaker, Heidi Döbeler. She is a forest scientist at the Northwest German Forest Research Station working in the Department of Forest Growth. She has long-term experience in developing silvicultural concepts under climate change and transferring knowledge into practice. The Ministry of Hesse in Germany has funded the project Maps for Climate Risk and Forest Development Types as an improved consulting foundation for new challenges for Hessian forest owners. It is part of the Integrated Climate Protection Plan in collaboration with the state-owned forests and the German Forest Owner Association for all types of forest ownership. During her presentation, she will provide insights on how to choose climate-adapted tree species and compositions for future mixed forest stands, a decision support tool for Hessian forest owners. Heidi, the floor is yours.
In my presentation, I'll give an overview of the results and a moment. Of the project with the title Maps for Climate Risk and Forest Development Types. The aim was to improve the consulting foundation for Hessian forest owners. My part in this were the silvicultural concepts and the knowledge transfer. This is a composition of the project. The Northwest German Forest Research Institute took care of climate scenarios, the water balance, nutrient balance, site growth, storm risk, and biotic risk. Behind all of these models are standing. And Hessen Forst is responsible for the state forest. And the Association of Hessian Forest Owners, they gave advice and basis data and a permanent evaluation. And now we are already in the phase of knowledge transfer and realization. In the first part, I will introduce you to climate change and its impact on forests. I will talk about site-adapted tree species and forest development types under different climate conditions. And in the second part, I present the web portal for operational use and the associated app, BEM Mobile. I think you know this all. This graphic shows two emission scenarios and the change of the global annual temperature. One is more optimistic and one is pessimistic. We work with this pessimistic one. The regional climate model we work with is roughly in the center within this range. We are already calculating with an ensemble of 7 regional models which cover this range. And with the next update, this will be implemented. We are interested in the effects of climate change in the vegetation period. The top half of the page shows the current climate, means 1981 to 2010. And the bottom half, the future climate, means 2041 to 2070. The temperature in Hesse rises from 15 degrees to 17 degrees, while the precipitation will decrease from 350 millimeters to 311 millimeters. It does not sound too bad, but precipitation minus potential evapotranspiration gives the climatic water balance. And the climatic water balance is negative today with minus 102 millimeters and is more negative in the future with minus 257 millimeters. The most important variable is the rise in temperature because it increases evaporation and it extends the vegetation period, and this is also taken into account. The next step was to quantify the water available to the plants in the vegetation period, and we chose the site water balance as an indicator for drought stress. It can be used for ground and tailwater-free forest sites, so-called terrestric sites. And it is calculated from the climatic water balance, means precipitation minus potential transpirations, and the usable field capacity, the available soil water for plants. To get the information about soil characteristics, the usual way is via forest site inventory. But only circa 80% of the area of Hessian forests are recorded. And furthermore, the recording is too little differentiated for our purposes. Thus, 2/3 of the nutrient estimations are mesotroph, and more than half of the water supply are grouped as fresh to very fresh. And we know this from comparisons with the National Forest Soil Inventory. for which soil profiles are evaluated and chemical analysis are carried out. So it was the aim to develop new models to close the gaps and to improve the existing maps. Summarize. We chose the site water balance as our indicator for drought stress. We calculated the climatic water balance for a future period, and we calculated the usable field capacity and the nutrient regime. How will the site water balance change on the climatic change, and how will this affect the tree species? This is the site water balance now under climate change. On the left side, calculated using measured data from the German Weather Service. The mean value for Hesse is 34 millimeters. This legend contains colors for site water balance classes from blue to red. It's getting warmer and drier. On the right side is the projection with the model stars 2. And the main value is minus 124 millimeters. Keep this number in mind for the next slide, please. Tree species possess different tolerances to drought, so they are grouped by threshold values for the expected risk of drought stress. We distinguished between low, medium, and high risk, displayed using traffic light colors, and just have a look at the row showing the values for high risk. The group spruce has a high risk from a value of minus 80 millimeters. The group beech from a value of minus 100 millimeters. And 124 millimeters is a forecast value for Hesse, so we can expect that even beech will have problems. But even at high risk, these threshold values are not absolute limits of existence or distribution. The values include mortality and also expected growth as an indicator of vitality. Please don't try to read this. Just want to show you this classification table. Here the tree species are listed. And here's a site water balance. And each site water balance class is divided into 6 nutrient levels. And what we did is we determined the position of each tree species in a mixed forest. So a tree species can be leading, mixed, or accompanied, or it can be excluded. Short summary, we classified tree species by risk of drought stress. We grouped tree species with regard to their status in mixed stands. Now, how do we get a recommendation for mixed tree species on a specific site? This is just background knowledge to understand. We can derive such ecograms from the classification table, and this, for example, for European larch. And the larch can be the leading tree species from mesotroph sites to richer sites, up to a site water balance of minus 200 millimeters. It can be mixed in these areas and accompanied by in this area. And in the gray one, it is excluded. So I am talking about forest development types already, but I will explain them later. This is how we get areas for planning, and I choose a very simple forest development type. It's FDT number 10, oak with beech or hornbeam. And first we look at the leading tree species. Oak can be sessile oak or English oak. What we do is we join the leading areas for the leading tree species. Then we look at the mixed tree species and we join the leading and mix area. And then we form the intersection. And so we get the area for FDT planning. Here's the trophy area and here the site water balance again. So why FDTs? Our central silvicultural concept for distribution and climate adaptation are mixed forest, site adapted and rich in structure under current and future conditions. And our basic assumptions are that disturbances often have a species or structure-specific effect. The species and structural diversity reduces susceptibility to disturbance and increase stability and resilience. And this is the front page of our catalog, which contains 32 forest development types. And a forest development type includes a general principle, a short information about the closeness to nature, as well as the function for protection and recreation, more practical for management and the production of wood, are target diameters, the period of production, and the proportions for tree species for regeneration and further development. And also the mode of mixture is given. And this is an extract from FDT catalog. There is always one page for every FDT, including the points mentioned and the graphic of areas for planning. That was already part 1. Now part 2. We come to the operational exercise, the web portal and the app BAM mobile. It's both freely available. And you reach our web portal, which is in German, I'm afraid, in just 3 steps. This is our home page. And there is a button, Baumartenempfehlung. And click first here, and then you have to choose the country, in this case Hesse, and with the third click you reach the web portal. There the OpenStreetMap will open, and you need to search your forest, zoom and click on the map. Then a window will open with information about the site, the FDT recommendations and the spectrum of suitable sites. Here a little bigger. If you zoom in deeper, we'll see all the polygons of the site water balance map. And here for detail, the numbers of the FDTs, they are linked with the catalog. There are also red numbers. These indicate FDTs with foreign tree species like Douglas fir or red oak. So forest owners get a warning that certification may result in restrictions. Well, another little detail, this blue point is in the graph is your chosen site. And there's the accompanying apps. There's one in Google Play and one in the App Store. And as a good thing, the most important advantage is the GPS localization. You needn't search for your forest, you just click in the map, name the site, and the selected site is stored in a list. A further click, and you get the detailed information. This is knowledge transfer, and it plays a central role, but it is a challenge. We use different ways, lectures, publications, instructional videos. And this is a knowledge transfer the way most forest owners prefer. We offer free training courses for forest owners in their forests, but it is a long way to establish such a new system. I would like to invite you to test the web portal, and you're welcome to give us your feedback. And I thank you for your attention.
Thank you also, Heidi, for this very clear presentation. I would like to continue already with the next speaker, that is Julia Schwarz. She's working at the Swiss Federal Research Institute as a researcher for silviculture and climate change. She's an up-and-coming scientist and expert in the field of ecology and management of forest ecosystems, focusing on short-term and long-term silvicultural strategies for adapting forests to the negative consequences of climate change. She will provide an overview under which circumstances thinning can or cannot help to adapt trees and forest stands to drought stress. The floor is yours, Julia.
Hello. Can you see my screen?
Yes, not in presentation mode yet.
Okay, good. Looks good. Okay, it might take a little while. I had this problem before. It will come up eventually. Sorry. This PowerPoint is troubling me today.
We're all familiar with the technical problem.
Yes. Yeah. Now you should be able to see it. Is that true?
Yes.
Okay, perfect. Thanks a lot. So thanks a lot for the invitation to talk today about the potential of thinning to increase drought tolerance of forests. Thank you also for the introduction, Julia. And I'm quite happy to talk about this topic. It's a little bit of an old topic for me. It has been kind of haunting me since my PhD, coming always back. And so I'm really glad to go back to this topic today. I structured the presentation today into three sections. First, relatively short one, where I will talk briefly about why thinning could be a suitable adaptation strategy in face of increasing drought risks in our forests. Then I will give a little bit of theoretical background relating on how thinning can potentially affect tree-water relations and therefore drought tolerance. And then I have a section on where I present, I make a summary of the evidence, what people have actually observed about thinning effects on the drought tolerance of trees. So by now, all of you are aware, we have the problem of increasing droughts. Our forests face these risks. So we observe drought-related mortality worldwide. And in many situations, we are especially worried about stands that could look, for instance, like this stand, so monocultures of relatively drought-sensitive species, in many situations coniferous ones, but it could be also beech and other broadleaf species. So we can distinguish between, in general, in between two broad categories of adaptation strategies. One of them is a bit more longer term, where we are concerned about the future stand composition. So basically, we are interested in introducing more drought-tolerant species into the drought-sensitive stands, either actively by underplanting or using natural regeneration if they're available. And then the aim is to have a future stand that is more mixed, consisting of drought-tolerant species and also structurally more rich. This is a long-term solution, and of course, this is very important, but we also have to think about existing stands, what to do with them, because in the short to medium term, the goal would be to stabilize trees in existing stands, and here, thinning is a very helpful tool. So now I will talk briefly about thinning, because I'm not aware if every one of you is familiar with the silvicultural strategy. In general, the goal of thinning in terms of silviculture would be that we promote selected trees, so fewer trees compared to unthinned stands. So we take out trees and promote those that we think are important. So they're more competitive, they're more vigorous. And nowadays, most of them would be showing also signs of a higher wood quality, if possible. So what we do, we simply take out trees and reduce the stand density. Here is an example for a spruce stand that was thinned the first time 30 years ago. And now you can see growth is really happening on these bigger trees now. Fewer, but more competitive ones. So by thinning, we want to increase the growth of trees by reducing the competition for all the resources. And this is simply shown here by the larger crowns the trees in the thin stands develop, because with these they can get more lights, and below ground they have more roots and can take up more nutrients and water. So now also a little bit more about thinning. I want to say that the thinning regime has to be characterized. This will come back later when we talk about the evidence. The most important component of a thinning regime is the type of thinning. So if you look into a thin stand, unthinned stand, that would be, for example, a monoculture of a broadleaf species. And then we have nowadays in most situations a so-called crown thinning happening that takes place from above. That is nowadays in most cases quite selective. So we select our trees that we want to promote. And then we start to thin out the trees from above. So the more competitive ones being the dominant and the co-dominant ones, and we select them from above. So we leave in the suppressed and intermediate trees. In opposition to this, especially in former times, thinning took place from below. So you took out suppressed intermediate trees. And if the thinning intensity was high, you would take even out some dominant ones. But you can see the consequences of both types of thinnings are very different. In this situation, your stand is still composed of similar age classes, but you have a higher vertical structure, whereas in this situation, you get homogeneous stands. So nowadays, this situation is more important. So now we talked in regards to the thinning regime about the type. It is also important to think about intensity of your thinning. In most situations, this is expressed as a reduction of basal area. So here is an example for a spruce stand in southern Germany that was at the age of 8 thinned for the first time. You can see in black, that's the control over time, the basal area of the control over time. And you can see the moderate thinning that took place here, here, and here. You can see that they did reduce the stem numbers, but still basal area was more or less similar to the control, whereas in an intense thinning, where the basal area was reduced a lot, you can see that they show a different trajectory of basal area over time, ending up at lower values. Then we have to think about the age at the first time of the intervention and the time since the first and the last thinning. You can see here this stand was thinned at an age of 8. This stand was thinned the first time at an age of 27. And depending on the age, the stands show a different responsiveness, simply because younger trees are more responsive. And for some species, this is only for a short time. And then this time since the first thinning, we have to separate short-term and long-term effects. I will talk about this later. And then the last component of a thinning regime would be the frequency. So in younger stands, you would entry, for instance, every 5 years, whereas if tree stands get older, you spread this to 10 years and intensity goes down at the same time. Now I'm going to switch to the actual topic. And before I actually talk about thinning effects on drought tolerance, I would like to talk about what actually determines the water balance in a forest and how then afterwards I will talk about how thinning affects the different components of the water balance. So what you see here is the water balance equation. What we are interested in when we talk about drought tolerance is basically the soil moisture, as you just heard also from previous presentation. So trees really need some kind of soil moisture to be able to grow. And then the question is, what determines the soil moisture? Of course, it's the precipitation coming in. And then from the precipitation, you have to subtract the evaporation from the canopy, but also the evaporation from the soil. And you have also to subtract the transpiration from the tree crowns and the transpiration from the understory. And in the end, you have to also consider runoff. Before talking about thinning, I would just like to point out from an example from a mature beech stand in Germany that this water balance looks very different in years with different drought stress. So if you look at a normal year, this plus means that we have a soil water surplus. So in this year, the soil water was getting more water than the trees used or the vegetation used. And in this case, it was because evapotranspiration was only 85% of rainfall, whereas in a dry year, we have a soil water deficit. And here, the main reason for this is that evapotranspiration was more than rainfall. So this components and this components outweighed what came in with rain. So just remember for now, water relations of stands differ under normal and dry conditions. And now I will talk about the actual thinning effects. And we talk first about very short-term effects after a recent thinning. So a stand looks, for instance, like this. So the entry just took place, everything is opened up, nothing really happened yet, seemingly. and we look at the stand level. So you just imagine there are fewer trees, maybe not this one is gone, but we have simply fewer trees. And of course, precipitation is not affected by thinning, but really several components are highly affected because fewer trees mean less leaf area for transpiration. It means less evaporation from the canopy, less interception, and therefore more throughfall. And in the end, in many situations, you will get a positive effect on soil moisture. However, this can be offset by negative effects of thinning, because if you have more solar radiation coming into the stand, this can lead to higher soil evaporation, and also more light means more understory growth and therefore more water consumption by ground vegetation. So therefore, in the end, I have to write this soil moisture effect into brackets because it really depends on how strong these components outweigh the reduction in evapotranspiration. And now you can see I put also brackets across this transpiration. This is because in some situations, transpiration at the stand level does not decrease after thinning because there are effects at the tree level we have to consider. So now we zoom in, you see a tree after thinning has more space, and having more space means having more resources, therefore reduced competition for resources. And what that means is that the fine roots expand really quickly. That can happen within very few years after the thinning. So this is a short-term effect. If the fine roots expand rapidly, this means the trees can take up more water from the soil. This increases stem conductivity, and in turn, it increases the transpiration at the tree level. And therefore, if an individual tree transpires more, it could mean that in a thin stand, sometimes the transpiration is not really lower compared to the control, potentially. And the question now is what happens over time? So over time, the trees grow. And of course, as I mentioned, in the thin stands, they should be growing larger crowns compared to the unthin stands. And the larger crowns mean more transpiration. They have larger root systems. Now all the structural roots are also larger. So overall, they have a higher water extraction capacity. And both of them result in higher growth rates. At the stand level, what does it mean? Again, the example with the spruce stand, that was thin 30 years ago. You can see in the heavy thin, we have stem numbers are reduced by 80% compared to the unthin stand. Basal area is reduced by 65%, but the leaf area is only 25% lower compared to this stand, meaning that at the stand level, the leaf area of the overstory does increase also relatively fast. In addition, we have to consider the leaf area of the understory, which depend on site conditions and so on, and species appearing, meaning that over time, the evapotranspiration will increase again since the last intervention. So summarizing the theoretical background is we now should think about when do the advantages appear and when do the disadvantages outweigh advantages. This depends on several things. It depends on the thinning regime, how strong and how often we thin. It depends on the site and climatic conditions, as these determine the drought severity, but it depends also on the stand. So meaning which species appear and which structural composition, what are the stand ages, and so on. So the question now is really, what is the evidence for all these effects? Today, I tried to summarize data from 4 meta-analyses. So each study that I'm referring to has analyzed already several studies. So it's basically a summary of a summary. The first study was thinning effects on hydrological processes. So for instance, evapotranspiration and soil moisture, published by Del Campo et al. 2 years ago. Then it's an older meta-analysis that I was lead author in. It's quite old by now. It was about tree performance during and after drought. We looked at growth response and other variables. And then 6 years later, Castanieri et al. Published another meta-analysis looking at the growth response, and they could now include many more studies compared to our study. So this is giving a much better idea about the growth response to drought and thinning effects. Finally, I'm really happy today to present also results from a paper that I'm also involved in by Julius Willig. It's currently under review. And this study, we look at drought-related mortality and the thinning effects. So whatever I'm showing now is trying to summarizing these studies. So summarizing the question how thinning affects water balance, tree growth, and mortality. So these are the main parameters of the four meta-analyses. So the meta-analysis on the hydrological processes provided clear evidence of thinning benefits because thinning did increase the net precipitation. So the precipitation minus interception. It did increase soil moisture a little bit by 14% in average. And it increased quite significantly tree level water use by more than 50%. In addition, there were some decreases appearing in stem flow that were high. And this is quite important, the transpiration was on average reduced by 40% compared to the unthinned stand. So what does this mean for the trees in terms of growth? It aligns quite well with the main results of the two meta-analyses looking at growth, because in these, it was found that thinning increases growth resistance. So it means that the thin stands produce growth less when it's dry compared to the unthinned stand. So they can maintain higher growth during a drought. And they can also recover their growth quicker after a drought has ceased compared to the unthinned stands. Aligning now it with the mortality results, the effects are also well aligned. Here you can see the main result from the mortality meta-analysis. The risk ratio here, you have to think that any value below 1 means that the mortality is lower in the thin stand compared to the unthinned stand. And this is quite nice. We can see now that in both the pre-drought and in the drought period, the mortality is indeed lower in thin stand. So altogether, we can say, yes, thinning does mitigate mortality and growth declines during drought. And this is possibly to a higher soil water availability and water extraction capacity. So this means that during a drought, the trees in denser stands, they experience much earlier and more extreme soil water limitations compared to trees in open stands. And this then results in lower growth and also in lower mortality. Then now the question that I put up before is about the intensity in the thinning, because now that we know, yes, there are benefits, but what is actually the best intensity of a thinning and how long do the effects last? So I will start again with the hydrological processes, because this is beyond what's happening to the trees. And very interesting, a very major result of the Del Campo analysis was that at a thinning intensity of about 50% of stand density, so reducing the stem numbers by 50%, this seems to be a very important threshold for significant changes in hydrological processes such as transpiration. And what we found also is that a moderate and a heavy thinning leads to higher growth levels throughout drought. You can see it here. You can see here the results from our old meta-analysis. You see here the drought year, the pre-drought years, and the post-drought years. The line at 1 is put there because any value above 1 means that the thin stand have higher growth compared to the unthinned stand. And what you can see, that both the moderate and the heavy thinning lead to higher tree growth levels throughout the drought period, including the drought year, but also benefits increase with thinning intensity. So the heavy thinning has 3 times higher growth levels as the moderate one when comparing it to the unthinned stand, sorry. So now, yes, that was the question about intensity. Now the question about how long do the effects last? Again, the results of Del Campo were quite important to understand first. And they found that the benefits for throughfall disappeared about circa 4 years later on after the thinning. The effects for soil moisture, the benefits for soil moisture and transpiration lasted a bit longer, and they found a maximum of 8 years of the thinning benefits. So, and then what does this mean for the tree growth? Now, the translation into tree growth is not so straightforward, because here a recent thinning can not only increase growth recovery, so meaning that the trees recover faster, but in some situation it seems to decrease growth recovery. And we think, and also Castaneri et al. Thought that this is probably due to an interaction with thinning intensity, meaning that in a heavy thinning, a recent thinning can decrease the recovery if it leads to really stressful conditions for the remaining trees in the drought, whereas the moderate thinning seems to be more beneficial. we're quite sure that this should be also affected by species and site. Then I try to summarize the effect on drought severity, and my conclusion is that drought severity matters, and I think possibly more even than the thinning regime. Why? This is based on the major results of Castagneri et al., because they found that during moderate droughts, yes, growth response is improved by thinning, but not so much during intense droughts, because here no thinning effects on growth response to drought happens. So this means that if a drought is not so severe, the trees in the more open stands, they seem to be able to access more soil water compared to thinned and denser stands, trees in denser stands. But if it's really in a severe drought, really none of the trees can access any more the soil water once it's depleted. This is quite straightforward. And what is also interesting is none of the studies looked at prolonged droughts. So it seems we now in our days, because we have more and more droughts appearing and they seem to be not more intense, but also prolonged, this should be really also analyzed in the future. And looking at these results, it should be really important. Then what determines drought severity is not only climatic conditions, but also the aridity of a site. I'm not going into details. I just want to mention in this recent mortality meta-analysis, we found the highest benefits for the continental sites. Again, values below 1 means that a thin stand has a lower mortality. And you see here clearly significant lower values for the continental sites. But looking at temperate and warm arid is a bit complicated by the fact that there are few studies. But at least we know for the continental site aridity, so benefits are really highest for mortality. And it's not only the geographic location that should matter, but we're quite aware that local site conditions are important. So something like topography, local soil conditions, or even microsite conditions, because all of these are known to affect drought severity and especially also how long a drought is maintained. The problem is that none of us could ever analyze this effect because the local site conditions are rarely reported and in many situations not even assessed. This is really a big problem. So finally, I looked into the effect of tree species and stand ages because we expect that different tree species should have a different drought tolerance and responsiveness to thinning. And we know from many other studies that tree response to drought is really species specific. A main result of the two meta-analysis was actually that we didn't find significant differences among tree species when looking at drought-related mortality in thinned and unthinned stand. And likewise, there were no significant effects of species on growth response to drought. You can see that here. So this here is the growth resistance during drought. In the lower part, you can see a positive effect of thinning, meaning that the lower density leads to smaller growth reductions during drought. In the upper part, it would be a negative effect. So the trees in the thin stands reduce growth more. And you can see here the most important species of this study. And just looking at the species of the genera of Quercus, which is considered quite drought tolerant, you can see really different effects of thinning. So even for the same genera, the thinning can lead to negative effects on growth resistance or positive, not neutral ones. Here again, I think the problem is that we cannot incorporate local conditions, something like when did the drought start? What is the species phenology at the site? What are the site characteristics, the soil conditions? If you could incorporate those, I'm pretty sure we would be able to really show the species effects. Finally, what about tree age? And for tree age, the summary is that the meta-analysis found either no effects at all of tree age or mixed effects. So meaning that the growth response to drought can either increase or decrease over age, and drought-related mortality was not affected by tree age. Therefore, I think this is again a problem about not being able to zoom in as we want to, because I think the age effects are possibly modified by the thinning regime. For instance, when was the age of the first intervention? How often was it thinned? And possibly also this depends again on the species that are present. Now I would like to summarize the extent of thinning benefits for drought tolerance of forests in a way that I found them when I look at all these studies. So it does really depend on the thinning regime, and it seems that repeated, so you have to go in quite regularly, and at least moderate thinning interventions seem to be most promising and seem to be a good compromise where the positive effects outweigh the negative ones of thinning. It's really important to consider climatic and site conditions. There are two things that we seem to be quite sure about. The benefits of thinning are larger during moderate droughts, and benefits are kind of disappearing during extreme droughts. And we're quite sure by now that the benefits are large in continental regions. Regarding effects of stand age and tree species, I showed you that the effects were really not consistent, and therefore it would be important in future studies that we could be able to consider, as I mentioned several times today, the local site conditions, but also stand conditions, and the climatic conditions in the pre and post-drought period, and how these factors are actually interacting. Because I think that's a big problem in most of the meta-analysis. It was not possible to include any interactions of predictive factors. So thank you from my side.
Thank you, Julia, for this great presentation. And we will now start with the panel discussions. So I would like to ask Heidi and Professor Kamen and Julia to share or to open their cameras, so to join the panel discussion. And actually, Julia, I think there are two rather quick questions from the audience, some technical questions. The first one is, maybe you can answer on the evapotranspiration calculation method that you used. Can you give an answer to that?
We didn't calculate evapotranspiration. Was it related to the evapotranspiration for this dry year versus wet year, I think? This was a study by Mark. They looked at stem flow. Yes.
Okay. Maybe, Mike, you can also catch up with that question if that answered your question. Otherwise, please specify another question. So then there has also been, again, a technical question to you, Julia. Can you quantify moderate and high thinning? Is 50% stem reduction moderate?
Yes, that's also a bit of a problem. So when looking even at the meta-analysis, it seems to be that people understand different things. In our situations, we said the 50% reduction would be so everything above 50 would be a heavy thinning in our situation.
Okay. Thank you very much for those clarifications. Now I'd like to involve Professor Kamen. So after listening now to Julia's presentation, is there also insights from your experience with beech? I do understand that, of course, thinnings are regarding also different stand age and so on. But have you also looked at the effects of the drought stress in beech, depending on the management procedures? Were there any information on those, on the management of these beech stands that were more heavily affected or less heavily affected?
So at our site, which is of course only a little bit less than 2 hectares, it's very difficult to add management as an additional treatment. But I think what it all boils down to, and we've seen this in Julia's talk, is the leaf area index. And I mean, that is a general and very important entity in all ecosystem models and also in hydraulic models. So essentially what thinning means is that you reduce the leaf area index, at least for a certain amount of time. And that is also something that we are seeing in our stands, where the trees that are experiencing drought stress. Now, I didn't talk about this today, but we artificially also introduced drought stress to some of our trees. We see decline in canopy and other in total leaf area. This is what, for example, also the two-fold exclusion experiment in Kransberg at the TU Munich has shown. And I think that is a very important morphological adjustment acclimation strategy of the trees to reduce vegetation impact. In general, if you look at vegetation patterns, you know, at larger scales, irrespective of forest or species, you can see that the leaf area index of an ecosystem is very finely tuned to the amount of available soil moisture and the evaporative demand of the atmosphere around the globe. And I think this is also how the most simple way of trees to actually respond to changes in moisture availability in our forests.
Thank you, it's clear. But still, I was wondering also, I'm not sure if I did understand you right, but I mean, there's quite a difference in the response still between the trees. So one tree stays quite healthy and the other one is severely affected. So why do mature trees enter these different pathways after a severe drought? Can you maybe respond to that?
Yes, so we saw this in particular for spruce trees, but we partly also see this for beech trees at our site, that the heterogeneity or the variability in the responses, especially to the 2018 drought, is quite large. So in spruce trees, we saw this very strong dichotomy that some trees had their entire vascular system damaged. And those are the trees that, as I said in my talk, died very, very rapidly, while other trees were able to keep their vascular system intact. And they were actually very healthy in the following season. I must admit, some of them got attacked by bark beetles, which is a different driver in mortality. But those trees that were not hit by bark beetles, they showed no sign of drought legacy effects whatsoever. And we believe, and we looked into this a little bit in more detail, tried to look at the growth history of the trees that were heavily affected during the 2018 drought and those trees that survived the 2018 drought. We did this in particular for spruce. And we could see that, very interestingly, these two cohorts, they behaved very similar with respect to their long-term growth until about 1950, so 70 years ago. And that's where the growth patterns of these cohorts, so you can easily look at that by dendrochronological analysis, that's where these growth patterns diverged, and the trees that then died in 2018 had, since the 1950s, a lower growth rate than the trees that survived. So what this tells us is that there are very small and subtle microhabitat differences that determine the fate of different individuals within a population.
Okay, thank you. That's an interesting idea, not idea, but information. And coming also to spruce, there has been a question also from the audience. One from Tom Locatelli, so from the UK, from Forest Research. One question about shallow rooting systems of beech and spruce. In my experience, spruce especially gets a bad reputation for the shallow depth of their rooting systems, but often this is due to shallow available rooting depth in the soil, rather than species-specific traits. Did you check for any correlations in available rooting depth and species?
Yeah, I think that's a little bit what I showed. I mean, there was also another comment that I saw that spruce trees can go down to 2 meters, and I doubt that. But I think if you compare that to other species, the majority of the water that spruce trees take up comes from the shallow soil. And we did this. We did these investigations using stable isotopes in soil water, both at natural abundance, and we also used tracer studies. And we did this at quite a few different sites. And all of these studies very clearly show that spruce trees are the trees that depend mostly on shallow soil water, beech trees as well. But then if you look at other species, they on average take up water from deeper soil layers. What's interesting, if you look at the variability in these data, for example, if you look at the relative soil water or soil depth where trees get their water from during a drought event, you can see that during wet conditions, also spruce and also oak and fraxinus, so the more deeper root species actually access most of that water from shallow soils. But as soon as the shallow soils dries out, these species have the ability to access deeper soil layers, while spruce is not. So we were able to show that very, very clearly. So spruce is constrained with respect to their water supply to the shallow soil. And it might be that there are a few deeper roots, but they are not sufficient to support the water demand of the entire canopy.
Thank you very much. Then I have one last question actually to you before I turn to the next speaker. During your talk, you were clearly highlighting that we shouldn't talk about the recovery, but that it is more important to look at acclimation potential of trees, right? So that we should more investigate what is the acclimation potential of trees. So do you think that following a drought event, we see that there's growth reduction, and this can be a long-term impairment when you are looking at growth only. But as an acclimation, it could be considered as an overall functioning and resistant to subsequent drought events. Do you have any comment on that? Maybe differentiating
the main
between
point that I
spruce
tried to
and
make is that,
beech.
if we look at 2018, and this is, I think, where 2018 differed, for example, from the 1947 event, or also from the 2003 event, is that we are now on a trajectory of change. And it's not that we had an isolated event where the conditions returned back to what I call normal afterwards, but we are on a slope of increasing temperatures and especially increasing vapor pressure deficit. So we must be very careful of treating 2018 as an isolated event. I think we are on a trajectory of change. So I think recovery can only happen if you go back to the status quo, which we are clearly not, and which we will not in the future. In fact, we are expecting to see even warmer and even drier conditions in the future. The patterns that I've shown you are very much in line with what climate models tell us. And there is enough evidence from physical climate models that tell us that what our future, on average at least, will look like with respect to temperature and vapor pressure deficit. Now, you asked about these effects leading to potential adjust physiological, anatomical, or maybe also morphological adjustments that might lead to a higher resistance or ability to better deal with these higher temperatures and lower atmospheric pressure. I think to some extent this is possible, and I think the main response is through morphological adjustments. I mean, we can actually aid these adjustments, and Julia has shown that in her talk by actually reducing the leaf area of a stand. And I think the individual trees themselves reduce their leaf area in response to drought. Leaves also become smaller, or you have less generation of needles, for example, when you look at spruce trees. But if you look, these changes have been now going on for 40 years. I mean, this is also what the climate data showed very clearly. And since we are still seeing a deterioration of the health of those of beech trees in particular, but also spruce trees, this tells me that over the last 40 years, the acclimation was not sufficient to deal with the current weather conditions. So I have my doubts that acclimation is sufficient to keep up with the relatively rapid changes that we're seeing.
Okay, thank you for this very grim future perspective, then also perhaps. Maybe Heidi, I can turn now to you. We learned from you about tools that can support forest owners and forest managers to choose tree species best suited for future climatic conditions. And you told us that this tool is freely accessible online. Have you been evaluating the use and how it has been used? So who are the stakeholders that are using it, and how has it been received in the area, in the forest, by the forest owners, for example? Any information on that?
Well, in the beginning, it was planned to get a systematical feedback each time someone uses the web portal, but that wasn't possible for data protection reasons. Of course, we have click numbers. They are increasing now by 270,000, and of course, app downloads. On our homepage, we ask for feedback, but this is seldom given. The feedback given during our training courses is positive. Some criticize the system as too complicated. The recommendations are part of the state subsidy, so forest owners have to use them. That seems to work. yeah.
Yes, but overall, this tool is, of course, only offering recommendations. It is informed by science on nutrient and water availability under climate change conditions. But it is also clear that this tool requires the correct interpretations of those recommendations. So the idea is that, from what I understand, that forest owners additionally always consult local foresters, from the forest administration, to receive full support to make use of these recommendations or to take part in trainings. So, but what if I do not consult a local forester? What could go wrong when interpreting the results without help?
Well, our recommendations are given for a specific site, but the silvicultural situation is not incorporated. So in most cases, forest owners can choose between some FTTs, and yeah, that is a problem that needs knowledge. And so it is advisable to ask a forester. Drought stress is only one criterion, and one has to consider many more. For example, if you can expect natural regeneration, and yes, so what can go wrong? You choose the wrong tree species composition, and they won't grow.
Okay, but then there's also a question actually from our colleague Julia here in the panel. Do you have any idea, because of course now we learned that this app or these recommendations are only used in Hesse. So there are other federal states in Germany that have different systems. Is there any plan to work at the national level to develop such an app solution for the suitable tree species, so for all of Germany? Do you have any information on that?
No, I'm afraid the countries have all their own solutions. Our research is only for the 4 northern countries, Schleswig-Holstein, Hesse, and Saxony-Anhalt. There is a system established already. And Schleswig-Holstein, that is the most modern way in Schleswig-Holstein. We recently put it online.
Great, thank you. Maybe, Julia, you can also add here from the Swiss experience. Do you have any information how it is in Switzerland in comparison?
I know about this tree app, and I know that this tree app is even being refined right now. So the tree app gives you an opportunity. It's at a punctual level, so it's not covering the entire area of Switzerland yet, but now they're working on it. And right now you can get punctual information about suitable tree species, and also the climatic scenarios are incorporated. So you can have a look at what is suitable now and then what is suitable in the future, based on RCP4 and then the RCP8 scenarios. So yes, I think in a few years it will be covering the entire Switzerland.
Nice. And you also had another question to Heidi. May I ask you to directly ask her? It was about the temperature, if temperature is also considered.
Yes. When you showed this graph, on the one hand it was the soil water balance, and then the edaphic conditions. No, what's it called? Sorry, I have to really go back now.
The trophy level?
The trophy level. Yes, exactly. And I thought where you say whether a species can be leading, at mixed, or disappearing.
Yes.
You know which graph I mean? Yes.
I think so.
And I was wondering whether you somehow can incorporate temperature raises as well there, because I could imagine that this graph looks like this now, but how would it look in the future when it's warmer?
No, it is for the future.
It is? Oh, sorry, then I didn't get that.
The climatic water balance we calculated for a future period, and
Okay,
that's in the site water balance incorporated.
Okay, sorry, I didn't get that.
Great. Then I would have a question also to you, Julia. So from you, we learned that forest thinning can help to improve the short to medium term adaptation of forests to drought stress, as it leads also to the changes in the tree water relations. Do you have like a general or maybe not so general recommendation to translate this knowledge now into forest practice? Have you been contacted maybe by forest foresters and been out in the forest. How do you deal with such questions? How to translate science into practice now?
Yes. I haven't been contacted. I think also I haven't been working on this topic lately. But from what all I could read, what seems to be really the best compromise are to go in repeatedly, so maybe more often, not every 10 years, but every 5 years, and do a moderate thinning, so not a really super intense one. I think this, from what I understood, this seems to be a really good compromise, and you would be on the safe side if you look at the negative effects. Yes.
But of course, we understood that this always depends on the tree species, the site and stand characteristics.
And especially the age. So now when we think about our beech forests, there seems to be now evidence that for older beech stands, a thinning could be even really leading to negative effects. So I think what we really need are more studies that really are designed more systematically and incorporate local conditions, because I'm pretty sure that the age and the species effects are really important to consider, but we are simply not able to do it right now.
Thank you. I would like to thank all the speakers now for joining the panel discussion. And I think now it is time that we continue with our second part of today's webinar. And I would like to ask Andreas Riegling to the floor now. Andreas Riegling is a professor of forest growth at the ETH Zurich and also at the Swiss Federal Research Institute. He's also co-organizer of this event, so thank you very much. And he has more than 30 years of experience studying the impact of changing environment on today's forests. His research focuses on forest ecosystem resilience with respect to climate change, biotic and abiotic stressors, natural disturbances, and legacy effects of past land use on today's forests. He's developing integrated forest management concepts to balance the delivery of multiple ecosystem services, including the promotion of biodiversity for our future forests. And today, he will present on the impact of mistletoe on Scots pine performance in a drier future. The floor is yours.
Thank you very much for this introduction, and thank you for inviting me. Do you see the presentation mode of my slides?
Yes.
Yes, perfect.
So I'm very happy to talk about mistletoe and Scots pine. So one of the starting points is a picture like this. This is from the Valais, where we have seen in the Valais, but also in many other European regions, we have seen repeated Scots pine mortality. Several studies could show that drought is always a key driver of these mortality events. But if you look carefully, then you see there is also mistletoes. On every second, or it depends on the situation, on many, many trees, we have severe mistletoe infection. This is not everybody the same. This is very severe in the Valais. This is also severe in southern France and in southern Spain. And it starts also becoming a problem in more northerly situated stands. So that's why I focus in the next some minutes on pine mistletoe. I give you a quick overview on the ecology of pine mistletoe, then I move to some results on physiology, on the impact on tree performance, and at the end, I look on forest dynamics and forest management. Okay, the ecology, what is special for mistletoe? That means it's a large group of plants. That means we have more than 1,000 mistletoe species worldwide. With Viscum, we have approximately 70 evergreen species. In Europe, of Viscum, we have 4 main species, and I will mainly talk about Viscum album, subspecies austriacum, which has its host Pinus species, Picea and Larix. And they have all in common that it's a hemiparasitic evergreen shrub growing on woody plants, and they take the water from the host plant and also some nutrients. But, and that's very important, they have their own photosynthesis. They are green, as you can see. Some spots on the ecology, especially is also the seeds. The seeds are ripening in winter, so hence winter temperature plays a role in a successful development of mistletoe. Then the seed distribution is done normally by birds. There is the mistle thrush, which is certainly a dominant one, yes. And then the seeds, the birds, they are regurgitated or excreted on the trees. And then they develop, for the germination, they develop a tube. and an adhesive disc here where they contact the cambium. So that means then they start growing in as a small individuum, or they can be really up to 30 years old and relatively big plants. It's not that they actively penetrate the plant. So that means they put their haustorium on the cambium, and then the tree is growing around. And after years, you can also see, if you make a cross-section, you can clearly define the moment of infection. What is interesting and also relevant for our discussion now is it's a light-demanding and a warm-loving plant. Hence, it is sensitive to climate change. So some words on physiology. That was a very nice study some years ago by Roman Zweifel. He analyzed the branches which were heavily infested by mistletoes, that's this one, or which are not heavy, but which were without any mistletoes. And then they analyzed the relative branch sap flow rate. So what you see here is a moderate dry day in the valley. You see the points they show the potential transpiration, and you clearly see that this branch which was heavily infested with mistletoes, he more or less followed the potential transpiration curve. But on the other side, the branch without any mistletoes, which is only pine needles, has a significant reduction already here when it is a moderate situation. If we go now to an extreme situation, the difference is becoming very clear. You see still the branch with a lot of mistletoes follows more or less the potential transpiration, but on the other side, sap flow of a branch without any mistletoe reduces significantly the sap flow rate. So that means mistletoe hardly regulates its stomata. They just keep them open. Pines regulate the stomata to reduce transpiration and to protect during drought. And as a consequence, pines, they have to compensate for the additional water loss caused by mistletoe by closing their own stomata. They also analyzed then the stomatal aperture. That means how open were the stomata during different degrees of soil drought. You see here towards the right, you have an increasing soil drought. They also did it for VPDs, that means for atmospheric drought, and it looks similar. What you see here, the black line, is a tree without any mistletoe. And then we have here 5% mistletoe, 10%, 20%, and very extreme 40% mistletoe. And you can see there is a strong reduction of the stomatal aperture if drought is increasing. And you see the difference becomes becomes very big if the trees are heavily infested with mistletoes. That means despite the reduced stomata opening, the total water loss of the branches with mistletoe increase. Mistletoe is increasing the drought stress for pine during drought, and I think that's a very key result. Then the closed stomata, of course, they reduce the assimilation of the pine up to 80%. So that means it really depends on the frequency of extreme dry days. And you can see that this will result in a significant reduction of assimilation, carbon assimilation. So the colleagues, Jan et al., they made a very interesting experiment. They said, okay, if mistletoe has an effect on physiology and on growth, let's see what happens if we cut the mistletoes. So they cut at several branches the mistletoes away and looked if this pruning has an effect on the host tree. And that's the result for pine shoot and also for the tree ring width. You see, this is the moment here where the mistletoes were cut, the pruning happened. This is the relative growth rate here, and you see there is an immediate reaction, and after 4 years, the difference became significant. And in the case of tree ring width, the same. We have an immediate reaction, a little bit softer, but also here after 5, 6, 7 years, the difference became significant. So this means if we take away the mistletoes, we see that we have an increase in the needle length, in the single needle area, nitrogen, soluble sugars, and also NSE concentration in the needles, and also the growth, annual growth rings, and the shoot growth increased. So as a clear indication of the effect of mistletoe on the performance of pine. So what is the impact now on the tree? We compared in a study mistletoe-infected trees and those which were heavily infected. And what we could show in few words is clear. That means the heavily infection or with increasing infection, we have a reduction in the branch diameter, we have a reduction in branch length, in ramification, in needle length, in needle ears, and in needle mass. So that means mistletoe infection has an immediate and a very strong impact on the architecture and on the assimilation capacity of a tree crown. There are interesting studies from Spain and from Turkey. They looked on the impact on the entire tree growth, and they distinguished between no mistletoes, moderate infection, and a severe infection. That means what you see on the picture would be a severe infection. And then they looked at basal area increment at the base at 1.30 dBH and also at the ground level. And what you can see that there is, of course, a significant difference in the growth if there is no mistletoe or if there is a heavy infestation at all levels visible. And what is also interesting, if you see the drought years here, these 3 lines, that means the difference becomes more significant always after the drought years. So also on the tree level, a clear indication. And then we come to mortality, which is at the end the most important parameter. We made a study. We analyzed for over 5 years the mortality rates in a monitoring plot. We distinguished between different crown transparency classes. So that means these are almost, fully vital trees with almost no defoliation. Then we have a middle category and we have a heavy defoliation category. Then we have no mistletoe in blue, few mistletoe, and yellow we have middle to heavy mistletoe infestation. We have the mortality here. So a very clear result for all transparency classes. So that means mistletoe infection really significantly increased the mortality risk of infested pines. Okay, just some impressions how it can look like in an extreme case. And I come to the last point. So consequences for forest dynamics and management. So if an infestation looks like this, it is clear that this might have consequences. There is a very nice study by the group of Granada, Meado et al., and they could show that mistletoe changes the amount, the quality, and the diversity of organic matter input beneath the host canopy directly on its nutrient-rich litter in comparison to pine litter, and indirectly also to a reduction of the host litter fall and an increase of the bird-derived debris, because the birds, they preferentially land on trees which are bigger and have less needles on it. So that means this the mistletoe infection promotes changes in the shrub, but also in the tree species composition. So it's not only, and in the negative side, it can also have, let's say, stimulating effects on the stand level. And then there is another study from Northern Spain by a French group, and they compared pure Pinus sylvestris stands with mixed Pinus sylvestris and maritime pine Pinus pinaster stands. And here you see the infestation percent of pines in the mixed or in the pure stands, and you can easily see you have significantly more in the pure stands. And they looked also on the tree height, on the relative tree height. That means if the pine, the Scots pine was taller than the rest of the stand, the infection risk was significantly higher. So that means the resistance against infestation was partly driven by relative tree height. The bigger the tree compared to the surrounding trees, the higher the risk for being infested. Okay, that's the summary. So Scots pine is increasingly suffering from hotter droughts, what also was explained for other tree species by Ansgar. Pine mistletoe is a hemiparasite depriving water and nutrients from its host tree. Mistletoes are currently increasing in abundance. I guess the following presentation will talk about this in more detail. And mistletoe infection, they alter the processes of tree performance, mostly in a negative way, but they have also some positive or can have positive effects on forest dynamics. And overall, mistletoe, they have the potential to alter forest dynamics and in the long term also to contribute to reshape our forests in structure and species composition. Thank you very much for your attention.
Thanks also to you, Andreas, for your great presentation. Now we have our last speaker for today, and he will give an insight on the perspective on mistletoe from Poland. So following now we have a presentation prepared by Wojciech Keciura and his colleague Roman Wojcik from the Institute of Forest Sciences at Warsaw University of Life Sciences. Roman Wojcik is an associate professor and has been involved in assessing the health and sanitary condition of forests for 32 years, and he developed a ground-based method for assessing the threat from mistletoe and is currently involved also in the development of a remote sensing method for assessing the threat to stands from pine mistletoe and fir mistletoe in Poland. Our speaker, Wojciech Keciura, is an assistant professor whose work involves nature modeling. As part of his research on mistletoe, he is conducting an inventory analyzing its impact on tree growth and investigating the feasibility of remote sensing identification of mistletoe. He is providing an update on the distribution of this tree parasite in Poland and the techniques used to detect mistletoe. The floor is yours.
Thank you, Julia. It's a pleasure being here. So together with Roman, we prepared a presentation. We'd like to take you on a tour on the problem with mistletoe in Poland, but it generalized more for Central Europe, I think. So when we started to dive into the problem like 8 years ago, when we asked foresters, do you see pine mistletoe on pine trees? Most of them would say like, it never happens, it's impossible. So we were thinking like, is it really a problem? Is this nice bush that we think of connect with Christmas is really making some trouble? And we started some literature review. We started to see that the problem is really there, but like it just started to be seen in Central Europe around 2015, 18. And we started also to dig more into the problem and try to think, okay, so if the problem is there, where exactly the problem is? Where should we think about it? So we did an analysis about the mistletoe range, and the black dots represent the pine mistletoe occurrence in different places in Europe. And the colored background are the different ranges of host trees. So the green one is Scots pine, the orange one is Pinus pinaster, so it's maritime pine, and the blue one is black pine. And as you can see here, the mistletoe is not growing everywhere where the host trees are growing. So we were thinking, okay, there might be, or there is some kind of other limiting factor that we don't see here, because Sweden is free of mistletoe with the data we had, or Portugal is the same situation. So we ran some analysis on the climate that is and connected it with the mistletoe range. And for current climatic conditions, we have found out that the Central Europe is most vulnerable for mistletoe infestation. Of course, the range of mistletoe is wider. It goes from Iberian Peninsula up to Sweden and to Balkans. But we started to think, okay, but all of us know that the climate change is happening, and we saw on the other presentations different scenarios that probably gonna happen with some probability. So we took 3 of them, the pessimistic, moderate, and optimistic, and checked what impact it's gonna give on mistletoe potential range. So if we go optimistic, we see that the mistletoe range moves a little bit north, so it starts to be more visible in Sweden and Baltic countries. If we go moderate, we see that it's similar here in Central and North Europe, but it goes off the Iberian Peninsula a little bit. And if we go more pessimistic, we see that it's really moving north. We see it already in Poland, in Central Europe, that it's already moved. So this will happen in next future. But mistletoe is one part of the equation here. The second part will be the host tree changes in the range. So current Scots pine range is visible here on the slide. And as you can see, the distribution is quite wide. But if we take into account future similar climate change scenarios, the red spots, the red area indicates problems for Scots pine and some limiting factors there. Of course, it doesn't mean that the Scots pine will disappear from them instantly, but it will suffer some problems with climatic conditions. We also heard about it in previous presentations of different species. So not only climate change will affect the growth of Scots pine, but also mistletoe will be, again, next factor that will make our forest more vulnerable. So we started to think then, okay, maybe like what kind of problem we are talking about here? Like, is it, I called it top or light problem. I will explain in a minute. So we done a study in central Poland, and we found that mistletoe prefers older stands, the more grown ones, with the time it needed to infestate probably, and it can get as high as 50% of trees infestated already. At the same time, it prefers lower soil fertility. We have hypothesized that it might be connected with lower nutrients amount, that trees are getting it harder to defend against the mistletoe infestation. We also checked, we went down from the forest level down to the tree level. So we found out, as you just heard, that the mistletoe is more looking for light, so it prefers taller trees. And at the same time, we found out something interesting. So it likes more sparse, not so dense grounds. We are not sure what was the first thing here. So was it mistletoe getting in and making the trees vulnerable, damaging the trees and making the crown defoliated? Or was it the first thing first? So the defoliated trees were picked up by, let's say, those birds that were mentioned in the previous presentation. This is still something we would like to dig more. But what we found, and what was interesting, that mistletoe in a bigger forest patch prefers the forest areas near the forest edge. It doesn't matter was it south or north, the edge trees and edge forest stands were more heavily infestated than the middle of the forest. And there's one possible explanation, so that's some birds that are the vector, the spread vector of the mistletoe, but the mistle thrush, which names coincides with the mistletoe itself, has one ecological, there's one problem with this explanation, because mistle thrush mostly lives in the central of the forest patch, forest complex. It's mostly territorial. It doesn't fly here and there, and therefore it's not the best explanation to why the mistletoe is growing on the edges of the forest. But of course, it's not the only one bird species that makes this kind of, is the vector here. So we found out that there are two more species that are connected with mistletoe dispersal. It will be field fir and song thrush, which are more connected with the ecotone, with the forest edge. They prefer to mix the field and the forest, and they live on this area. So they might be one of the vectors that give this bigger amount of mistletoe on the edge. And at the same time, we have to remember that in the recent years, the winters are not so severe as they were a couple of years they were in the past. So the birds are not migrating that much. It means that they stay in the forest longer, stay during the winter, and winter time is the moment in which the fruits of mistletoe are getting mature. So this might make the problem even worse. But next, we started to think, okay, we do this kind of ground assessment. So do we see the whole problem? When we look from the ground level with binoculars, do we see all the mistletoe that that is there in the forest? So we took a heavily infested forest stand. We measured all the mistletoes there. 6 or more means here that we cannot distinguish if there were, how many mistletoes exactly were there, but the numbers were like 6, 7, 8, maybe 9 or 10. But sometimes because of the crowns, you cannot see from every angle you would like to see. So we had to assess this in this kind of categories. But what we also found that those mistletoes that we've seen from the ground level were occupying mostly the top and the middle part of the crown. And then we cut down some trees to check, okay, what is the exact number of mistletoe? And we found out that on one tree, it can get as high as 289. Of course, most of them were small ones, 2, 3, 4 years old, that were growing on the top of the branch. So where they were not visible from the ground level, but still the problem exists. Sometimes we were not able to see even 50 centimeters mistletoe because they were hiding behind the others that we could not distinguish which one is which. And more interestingly, most of them, mostly the small ones, are growing in the middle of the crown. Probably this has something to do with this bird hypothesis. Okay, so maybe we need some kind of different perspective to see the problem here. We started to analyze some drone aerial footage. We did the inventory of trees and then tried to compare the ground observation with also drone photos. And we found out that the mistletoe is visible from the top. And as you can see, it grows. I mean, it grows on the tops, as we mentioned before, but also it's easily visible there because if it grows under some branches, it's not that easily to detect. But at the same time, we found out that the needles, color of the needles, and color of the mistletoe leaves on some regions and some times of the year are getting more and more similar. So we have to be very careful in searching for these. But we are now currently developing this method, and we hope that this will give us a better perspective on the advances of mistletoe, and we would like to have this method done to be able to monitor it and take some do some management with it. So take-home message. Mistletoe is spreading to the north already, and it will be spreading more due to climate change. It likes trees that provide more light, and it's more abundant near forest edge. There is much more mistletoe on a tree that we can see from the ground level, so we underestimating it. And we hope that it can be easily detected using remote sensing and will give us some benefits here in the future. Thank you.
Thank you very much. Thanks to both of you. I think now we have a good, solid, basic understanding of mistletoe, what it likes on trees, taller trees and more light, and how it is spread. So now I would like to start with a short panel discussion also on this topic, because I think it's actually really nice. And this cross-border communication that we enable today between Swiss experience and the Polish experience, and the sharing of experiences, because this is going to be the core business of a future forest risk facility. So I'm really happy that we now have the chance to experience forest risk already in action before its full-scale launch next year, and fostering the transboundary exchange now during this following panel discussion. I would like to start asking Andreas if he, from his experience, has anything to add to the Polish experience. Have you also started remote sensing, for example, in Switzerland?
Yes, first of all, I'm very happy to see the results from Poland, and they fully match also our experience. That means they are fully in line. And I also can only say that means I was traveling in the past years also to the north, to northern Germany, to Poland, and there we have seen some initial cells of mistletoe, and now I get exactly the feedback what you gave. That means now it seems to spread and to increase in its range also to the north. So that means I think we would need to have let's say, a study which demonstrates this, let's say, this spreading towards the north would be very interesting. Well, we have a research group at WSL, which is dealing with remote sensing, and they are able to also to identify, but there was not yet a project on this topic. So that means this might be really interesting. I do agree. This has a high potential.
Thank you very much. And there have been 2 questions from the audience also to you, Andreas. Maybe you can respond to those. And the first question is, what climatic factors limit the spread of this subspecies of mistletoe? The question is from the UK, and it was stated that they also have Viscum album in the UK, but rarely on pine. And generally, it's not a species that is reported as causing problems for any tree species in a forest context.
Mm-hmm. Yeah, I think it's mainly the winter temperatures, because seed ripening happens, as also Wojciech said, happens in winter, and seed ripening, if with increasing temperatures, might be more successful. But that's only one factor, and the other factor was also mentioned by you, Wojciech. That means we need to have the birds, the vectors there, and there are no strong studies on it. But I have indication also from grey literature, which say that the mistletoe thrush in the past, they migrated in winter to the south, and now probably with climate change, there might be other factors, they do less migrate. That means there are more birds staying over winter in at least in the Valais in Switzerland, in this dry valley, and this, of course, these 2 combinations with an increased, or let's say a better seed ripening and the availability of the vector, I think these are the main factors why there is a spreading. Why it is not happening, or it's not really already there in the UK, I don't know. Probably it's also perhaps the question of the vector. I don't know if this is the reason. But I think there are no climatic, according to my opinion, there are no climatic reasons, or also no site conditions why this should not be the case also in Great Britain.
Thank you for this answer. And second question, how do you explain that mistletoe infestations increase mortality irrespective of crown defoliation levels?
Yeah, well, I think this simply shows how important or how severe the factor is. That means if you really have severe mistletoe infestations, not only 1 or 2 small ones somewhere in the crown, but if you really have severe infestation rates, then the negative consequences or the impact on the tree performance is there, independent if the tree is in addition weakened by needle loss or not. I think that's the only explanation I can give.
Wojciech, feel free also to add if you have from your experience. Otherwise, I do have a question also from the audience, but also that is in line with what we have heard. So we heard that there is more infestations at the pure stand level. So if there is no mixing of tree species, and that the pine trees are more infested. So also the question is, have you checked how it is looking in mixed species stands? Is it I mean, how is it? Is there a percentage you can give that the infections, it takes, for example, longer for pine trees to be infested, or are there any numbers that you can give for mixed tree stands?
Well, from our experience, we didn't see that connection between mixed and pure pine stands. So, but we are still running our project, so maybe we'll get some more results this year. But maybe, I don't know, Andreas, maybe you have some thoughts on this.
I think it's the only study I know is the one I presented from France and northern Spain, which is, of course, it's a special situation. It's Pinus sylvestris and Pinus it's maritime pine, Brucia. So that means it's not really a mixed forest we could imagine. But overall, I think it just from my system understanding, it's clear that if you have an increased number of different tree species, the risk for the single tree species being infested, be it with mistletoe or with another pest or diseases, is reduced. I think that's pure mathematics. I think that's clear. So that means that's another indication of increasing the number of tree species in our stands. And the other thing, which they analyzed there, is also makes sense. It makes also sense in respect what Wojciech said. So that means the birds, they are flying to their trees, and that means they go to the trees which are exposed, be it at the edge or be they a little bit bigger than the rest of the crown, because they can fly there. They obviously like it. And also what we also have seen, there is a connection that those trees which were more defoliated, the birds prefer to go there because probably it's better to land there. So it must be connected to the vector of the birds. So I think stand structure and mixing are the arguments. And I think, because I come from mortality research, and I have seen mistletoe always as a negative aspect, as a contributing factor, which is the case, of course. But on the other side, I see that means when we go to a more holistic view or on a landscape view, then we need to think of, perhaps there might also be beneficials. That means we can perhaps also profit from it. Of course, it's a difference. If you have a managed forest where you focus on pine, then you might have a problem in the future. But this might be an indication that perhaps you need to mix a little bit, not only to have the pure pine forests.
Thank you very much. And I would like to go back to the Polish colleague also. Since we heard that basically pine stands are still the dominant tree species in Poland, and the problem with mistletoe in pine stands has only become a major problem in the past 10 years. And how is the forest management and forestry sector in Poland reacting to this problem?
So I think they are not fully aware yet. We try to raise the awareness, and we are also grateful to be here to do it on broader scale, because I think the problem is not only Poland. In Poland, or it's more Central European, where Scots pine is one of the major species. And Poland is the best example because we have like 60% of trees that are Scots pine. So it means that if the problem will rise, we'll need to face it. And there are not many management techniques we can use. So of course we can cut down trees that are infested, but then we saw that cutting down trees, if we do too much thinning, it gives some other unwanted results in the forest. We can, we sometimes, if it's old stand and if the trees are heavily infested, we do clear cuttings. So we just speed them up a little bit, just to be sure we can get rid of the problem. But the problem is migrating here and there. So we would end up in cutting almost everything eventually, because we are now working on a paper that will focus on the spread of the mistletoe in Poland, and we have some results that it's almost 2/3 of the country. So 60% of the Scots pine stands are somehow vulnerable to mistletoe. So we can all, like Andreas said, we can do the pruning, but it's very expensive in terms of the forestry. I mean, we can do it on single, veteran trees that are very important for the ecology, but probably not on the stand or forest levels. So we are very limited here, and we cannot use any chemicals, and there are not many biological agents that would help us. There are some findings about new fungi or some insects that would attack mistletoe, but this is not the big thing here. They don't do much harm. So I think we would need to focus on this. So one option would be to rebuild the stands, as Andreas just mentioned. So more tree species, if it's really the connection, the more mixed the stand, the more the better it can defend against mistletoe. Then we are in good line, because we are rebuilding stands in Central Europe for many years. So this should help a little bit. But if those climatic projections gonna end up as they say, so if we will have big problems with drought and with mistletoe at the same time, I think we need to make a bigger discussion about it, and we need to think more, because we don't see any easy solution here. And that's maybe pessimistic at the end of this webinar, but we're still not sure what to do. We have some funny stories, like we were doing some experiments. There were a lot of mistletoe on a tree. So after we cut it down, we wait, like it was the evening. The next day we planned to get the mistletoe from the tree and it was gone, like nothing left. Deer came and it ate all of it during the night. Probably because of the high amount of sugars or some other nutrients there. So we cannot put deer up to the crowns, but maybe this would be one option. But for sure, what we need and what would be the most important here, we need to know where the problem is. So that's why we focused on the remote sensing thing, because otherwise we are not able to monitor this every year. And this will be very important, especially with the combination of the with one of the presentations showing the drought problem, that it's not only separate event, it's making a series of droughts. Of course, some regions are suffering more and others are getting not so bad, but still the problem is arising. We see the similar patterns in the whole Europe. So we need to focus what to do and solve the question.
Yes, thank you very much. I really like the idea of putting the deer to the crowns. I think this would solve also heavy browsing problems all over Europe. Hopefully, it would be a good idea. And thank you also. I think this has been a really nice concluding statement also. And since we are actually at the end of this webinar and at the end of our time for today, I would like to come to an end today. I would like to express my thanks to all the speakers for their great presentations, for the chance to raise questions, for the open exchange and fruitful discussions today. Thank you very much. And to the audience, please remember we will also share the streaming, the recording of this event and summary, as well as the presentations on our webpage. So I also want to thank the audience for listening and for their active participation. And of course, last but not least, thanks to my colleagues for supporting me. And sorry for the hassle in the beginning with the connection. I feel this is a modern, normal, everyday problem now with online webinars, connecting problems and technical issues. So sorry for the trouble at the beginning. And please remember, feel free to reach out to us if you want to get involved with ForRisk, with the Forest Risk Facility. We're looking forward to your connection to us. Thank you very much. So I hope you will have a good lunchtime now. Enjoy your lunch and see you soon for the next webinar.